Okay, so I'm finally ready to begin the MOS planning session to start talking about that. Hopefully everybody's here for that. What I'm going to do is run through a series of slides to introduce the MSA planning tool to you and some aspects of sort of the workflow for you for proposing for MOS observations. And then I'm going to give the demo afterwards. I'm going to try not to speak too much to each of the slides so we can get through this session a little bit. But if you have any questions, please let me know and ask. So the planning tool was under development for many years, and it's been a team effort. So these are the team members that I'm recognizing right now as working on, having worked on it. Some of them are here. It was based on an original prototype by Klaus Pontoppidan, who also did the IDL prototype, did the ETC prototype. So this is the organization of my little talk here. I'm going to do a process overview of the MOS observing process. I'm going to talk about characteristics of the MSA that impact MOS observations and sort of the rationale for creating the MSA planning tool. I'm going to say a few words about target acquisition and some considerations about pre-imaging. Then I'm going to give a brief introduction into the tool itself, talk about the input catalog and candidate lists that have to be created, and then key planning parameters as well. And then I'm going to give finally the demo. And so there'll be questions and answers after that, I guess, or anytime, really. Okay, MOS process overview. So the main point here of this slide is that unlike most JWST instrument processes, we have to adopt a two-phase approach for MOS observations. And the reason for that is that we need the flexibility to assign an orientation to your programs, to your MOS programs, in order to get them spread out on the long-range plan. So there are two times during which you'll be using the MSA planning tool to prepare your observations. Once for the submission deadline, and I think I have a nice big cursor here that you can see. That's the red star here, the proposal submission deadline. So you'll be working with MPT. And the reason you need to do this is because we actually need planning visits in order to place those prospective visits or potential visits on the long-range plan and to develop a plan for everybody's observations and determine an orientation angle for your MOS observations for you. So that's the first step. And the reason that you will want to use the MSA planning tool is that you have to request an exposure time. And the exposure time that you determine, the overall requested time, will depend to a great degree on your observation strategy. So you'll want to explore all the parameters of the MSA planning tool in order to see what works best for your science. And so that will break visits out in different ways potentially and have an impact to the exposure time request that you have to submit. I have a bar in here showing a Nearcam pre-imaging, and that's optional. We'll talk a little bit about that when I talk about target acquisition and the kind of accuracies that are needed to do MOS planning. The second time that we need to use the MSA planning tool is to prepare our final observations. Once we have those Nearcam observations, if you're getting them, and you have a fixed orient assigned to your program, then you have to do the final program development. So you'll be using the MPT in earnest at that point to develop actual programs, with pointings that are going to be executed on the telescope. So the MSA planning tool uses the shutter status information. This is one thing I wanted to say here. The MSA is built of 4 quadrants. Maybe I have a picture of that here. 4 MSA quadrants, actually. I got rid of it. Here it is. 4 MSA quadrants, each with about 65,000 shutters. And so they're configurable, independently configurable. But of course, there are, failed shutters. That's what the real MSA looks like. So these black areas here are failed closed shutters, for example. But I've jumped ahead, so I wanted to just give you an overview of the process first. So the final planning here will take all of that into account. And you'll want to do that final planning with the latest, greatest shutter status file. So that means you probably want to wait as long as possible, but don't wait too long, because it is a process, and it takes a lot of learning. I would say there's a ramp there. Okay. So MSA characteristics. The 4 quadrants are composed of these really tiny MSA shutters that are about 200 by 450 milliarc seconds on the sky. So very, very small, and you're creating these little slits on each of the sources in your field of view, your field of interest. The shutters are separated by these little MSA bars that vignette the light from in front of them, so onto the detectors. So, and they actually cut off even a point spread function. You don't receive all of the light from the point spread function in the one shutter. There's also a gap. This is a projection of those 4 MSA quadrants, the MSA aperture, onto the 2 detectors, which are behind shown here behind the 4 MSA quadrants. And so you can see like the little IFU and the fixed slits are here. And the whole field is about 3.5 arc minutes by 3.5 arc minutes. And there is most notably a gap of about 20 arc seconds between the 2 detectors. So if you don't have more than 1 pointing on your objects, you are going to have a gap, most likely, in your medium or high resolution spectra. You're going to see a gap of wavelengths. So you really want to observe using dithering is probably what you want to do. Okay, so also the source positions at the aperture, at the entrance aperture, at these slits, are going to require some knowledge about the 4 optics and how that creates a geometrical, optical transformation to that plane. So we have all of that. We have that entire model in our MSA planning tool, and the tool takes care of that for you. It maps those sources from the sky to the MSA plane with the optical distortions. And there's additionally a telescope velocity, velocity aberration that occurs that causes a scale effect at the MSA plane as well. So all the target positions that we're working with will have been, corrected for these effects at the MSA. I've mentioned before the MSA has these failed shutters. There's also shorted rows and columns, and the planning tool plans around all of that, so it doesn't use those bad columns. At a later date, if there is an impact to your program, once you've planned the final program, if there's an impact due to a change in the shutter status, we'll notify you, and you may be asked if you want to replan those observations. Hopefully, we won't have that. We won't have the shutter status evolve too rapidly, but we have to wait and see on orbit. Again, you'll want to dither to cover the gap and to mitigate any detector artifacts. And typically, most programs, I would bet, would probably want to observe the same sources at every dither point. So that's another thing that the tool does for you. It tries to, it tries to create pointings where you can recover as many sources as possible and match those sources at all pointings. So the deliverables from MPT, the MSA planning tool, are pointings, the corresponding MSA configurations, and a set of observed targets in the end that you'll observe. Okay, a word about target acquisition and pre-imaging. So there are going to be several choices when APT 25.4 comes out for your target. Right now there's 3 choices, 2 of which are point and shoot, essentially. That's the none option and the verify only option. And they deliver, I think, for most programs, a somewhat inadequate pointing accuracy of about 100 milliarc seconds. In one case, you take an image, and in the other case, you don't take an image. So you can, in the case where you do take an image, you can potentially back out what the pointing was. I'm going to talk about the MSATA because I think that's going to be typical. And MSA target acquisition is the standard method for target acquisition, and it's done with 5 to 20 reference SARs. The catalog of reference stars and actually the catalog of sources has to have a relative astrometric accuracy between 15 to 20 milliarc seconds in order to take the best advantage of planning sources accurately within these tiny little slitlets. So the process is that the TA takes 2 images and gets the centroids of these reference stars in those images, and then calculates what the little offsets have that have to be applied to the targets, to basically to the scene, basically, or to the telescope to move it where it needs to be for that MSA configuration. Each visit will have to have 5 to 20 reference stars. So this is done at the visit level, and it has to be done after the plans are developed and the observations are created. So it's done at the visit level. Let's see. And so for that reason, it needs to happen after the orient is assigned. So it will happen at the flight update program deadline, so at the second deadline that I was talking about earlier. And we're working on a detailed script that will help provide or choose candidate reference stars from the catalog that you provide, and we'll come up with the magnitudes and the NIRSpec filters that are needed as part of the selection process for the final TA reference stars that are used. So one point is that the catalog should contain as many candidate TA reference stars as possible when you finally do this at the flight update stage. And it should be over an area that gives a little wiggle room in terms of pointing choices to the MSA planning tool. So I always say about 5 arc minutes by 5 arc minutes is the best, I think. And so if you require this level of accuracy, you can get that from HST data, 15 to 20 milliarc seconds is what's needed, delivered after the TA. You need to start with a catalog that is derived from either HST data or from Nearcam pre-imaging in order to get that level of accuracy. So that's a consideration about whether or not you want to propose Nearcam observations within your, with the NIRSpec follow-up observations as part of your same program. But for the Nearcam observation part, if you decide to do this, that has to be fully specified at submission, at proposal submission. So this is just a plot showing the delivered pointing accuracy on the left side axis here as a function of the catalog astrometric accuracy. And so the real point here is that to be in this optimal regime here for TA accuracy, you have to be working with Nearcam or HST data, as I said before. Let's see, what else did I want to say here? Okay, I think that covers that slide. There is a tool written by Leonardo Ubeda on the NIRSpec team that will help you to visualize any Nearcam pre-imaging mosaic that you design on top of your MSA pointings that you derive with the MSA planning tool. So it's just a useful tool to have. There's a JDocs page for it that I've included in the slide here. So the slides are all going to be archived. You can go back and read them for the actual detailed information. This is just showing a particular mosaic of Nearcam that might work for some observations. Okay, so let's talk about the MSA planning tool in APT a little bit. I'll give you a general description of what it does and how it works. So the user has to upload a catalog. It works with a catalog. So you have to have points in the catalog. There are whatever sources of interest that you have, but we'd like the catalog to be as complete as possible. If eventually you would like to see if there's contaminants contaminating your slitlets, it's important to have a very complete catalog in the beginning. Okay, so from the catalog you will derive 1 or 2 candidate lists, and that they're your primary sources, and then what we're calling filler sources, really secondary sources, I would say. And the difference, I'll talk a little bit about the difference between those 2 types of sources in another slide. So the user will select an aperture position angle to run the tool. You select an aperture position angle that is one of your feasible angles that was delivered to you by looking at the general TVT tool that you were shown. You'll specify a default slit shape on your sources, and I'm going to talk a little bit more about all of these parameters, but a centering constraint will have to be specified, and then whatever set of dithers you want to do will have to be specified as well. And then MPT will create a grid of test pointings over the area of your primary candidate list, and it will be to your specification with the step size that you specify in the tool. And then it will test each pointing, and it will sum the weights of your targets. If you decide to use weights in your planning, it will sum the weights of all the targets that it can stuff into the MSA in operable shutters at that pointing. Now here, I wanted to point out that the top-down ordering of sources within your catalog actually matters, because when it's going to build the MSA configuration and to determine how many sources it can get into that configuration, it starts at the top of the list. It just adds sources into operable shutters one at a time. So the ordering matters. The set of pointings with the largest score is the one that's going to be chosen for you, and that's going to be the optimal set of pointings for your dithers. And as I said before, the products of MPT are the pointings, a target set that it's going to give to you, and MSA configuration. So if you really want certain targets to be observed, they have to be in the primary list, because it's the primary list that uses the target weights, and you have to have an appropriately valued weight given to those targets relative to other targets in your list. Okay, so now let's talk about the input catalog and candidate list a little bit more. So there's an example here of an input catalog. It's simply an ASCII formatted file. It can have a single line header at the top, marked with a hash symbol or a pound symbol on the left. And then the names of the columns are in that header line. And that's optional, like I said. And then commonly included column types that are automatically recognized by the tool are the ones that you see in here. My arrow's not showing up for some reason. Right here. So it's target ID, for example, RA, DEC, magnitude, a magnitude error. I think it's called flux uncertainty. Redshift and weight, those are commonly recognized columns that automatically get recognized. But you can work with any information that you have in your catalog and decide to use that as a working column within the MSA planning tool. For people that are adding reference stars, when you do the final reference star information in your catalog, again, I said it would be done with the script that we're developing, so you don't need to know too much about this right now. In the end, you'll have all of these added columns that will say that these objects in this column are, it'll be true or false, whether or not you can use it as a candidate reference star in your planning. And so the next step is then to have the MSA planning tool vet the positions of those reference stars to make sure they're in operable shutters as well. So it's kind of a two-step process, the script followed by MPT checking the reference stars. Okay, so again, the primary candidates are simply your favorite sources that you want to observe, weighted accordingly within that list. The filler candidates are just filling up they're used to fill up the regions of the MSA that were not otherwise used by those primary candidates. It's to basically improve the efficiency of your observations. But the target weights for the fillers are actually not used. So if there's anything that you really want, it better be in the primary list with an appropriate weight. Okay. Yes? The weights, you can have them in the catalog, but the weights are not, they don't factor into the choice of the plan, the best plan. Yes. You can optionally choose to use the weighting that's in the catalog, and that's only used with the primaries. We just sum the weights for the primaries when we determine the pointings. Yeah. So it's only the primaries that determine the best pointings. Okay, I think I have one or two more slides before the demo, so I'll try to go through these quickly. As I said before, the shutters are very small, about 200 by 460 milliarc seconds on the inside of the bars. This is showing one shutter with a perfectly centered source inside. But there are 4 choices of slit shape that you can choose as your default slit shape for the planning, for the MSA plan. And they're 1, 2, 3, or 5 shutters. If you do just a single pointing, the target will be in the center of the slitlet. It will be in the central shutter of the slitlet. Of course, targets are positioned wherever they're positioned, so you can't, there's no way to guarantee that the source will be at the center of the shutter in each exposure. Of course, you can have many sources that are not, and so many sources will suffer from some slit losses. The background measurements in a single pointing are basically taken from any other shutters that are not occupied by a target. And I've mentioned before that in order to be able to check for contamination in those slitlets, you have to have a complete catalog. Okay, this is just I wanted to mention a couple of posters that are out there now that would be useful for guiding your parameter selection. Emily Wazlowski has a poster out there that looks sort of like this. And then there's one by Leonardo Ubeda on that tool that I mentioned about the visualization tool of the NIRSpec and Nearcam. It's out there. Another key planning parameter in the MSA planning tool is the source centering constraint. Let's see. So there are 5 choices for the source centering constraint. And this is allowing you some flexibility to limit the slit losses by setting a margin within the shutter within which you want to find your sources. It just basically excludes anything that's outside that margin from consideration in the MSA configuration. So it's very, very easy to understand how it works. It's not a one-to-one translation between, I mean, as you might imagine, you might lose some efficiency in doing this, but it's really not a one-to-one translation between those 2 factors. It depends on your source density in your catalog. If there's another source available nearby that can utilize that area of the MSA and be within the margin that you set, it's possible to do that. So you don't necessarily lose efficiency, but this is why you need to play with the different parameters to explore them. This is just showing the wavelength-dependent slit throughput versus those different choices of centering parameters. And to make use of this knob in MPT, you really have to have very high relative accuracy in your catalog, 15 milliarc seconds or so. So this is basically saying you have to use HST data or the Nearcam pre-imaging. Let's see, another one is nodding, dithering, and background subtraction I want to talk about. So nodding is where we move the telescope slightly up and down to place the target into different shutters. And it's basically like a low-cost dithering because you don't require an MSA reconfiguration in order to accomplish it. It just uses the same MSA configuration and just nods. So you get, in the case of a 3-shutter slit, you'll get 3 exposures. 3 distinct exposures. I've shown another example down here with a 5-shutter slitlet that you might use on a more extended target. And there's actually 2 options with that selection. You can get 5 different exposures, or you can just have the nodding occur between the central shutter and the 2 extreme shutters, and you get 3 exposures in that case. It's a choice that you have. In addition to nodding, you can actually apply a primary dither. So you can move the telescope over, say, in dispersion, for example, or in spatial axis. You specify whatever separations you want. You would do this in the case of trying to bridge the gap between the 2 detectors. You would specify a 20 arc second dispersion separation, in this case, a dither of 20 arc seconds in the dispersion direction. And so what I've shown here, in this case, if you chose both nodding and this primary dither, you'd get another set of 3 exposures on the backside. And then background subtraction occurs, it depends actually if you have a single pointing or if you choose to do the nodding. The background subtraction in the single pointing uses the shutters that do not have the target in them to estimate the background, and those get co-added and then subtracted from the target spectrum. With nods, though, you're actually making use of all of the background shutters in all of the 3 exposures. Okay, so let's go to the demo. Let me get escape here. I think I need this. And I need to bring up, excuse me, APT. I'm using I think the current version that's released, 25.2.3, which is what you should have, I believe. And I think you've learned enough about these buttons up here, so I'm just going to go and create a new JWST program if I can. This is not working. There we go. Okay, like Jeff, I'm going to ignore all the red X's. I'm going to go just to the ones that are relevant for this test. Yay! Okay, so click over. I have to mention that this is done completely different. The MSA planning tool runs completely differently than you would normally specify an observation in APT. Normally, you would go to the observation template and start from there and specify your observation. I think Jeff and others showed you how to do that. But for MOS planning, what we do is we go to the observation folder. We create a new observation folder. And it looks like that. It says observation folder. And it already has an observation in it, but it has a red X next to it because there's nothing in it. We're going to want to delete that because MPT creates its own, but let's leave it there for now. We'll do the minimum here. We click over to the MSA Planning Tool tab. And now you can see that we have our planning tool is organized into 3 different areas: catalogs, planner, and plans. Right now I'm in the catalogs area, and I'm going to import my catalog, source catalog. And it's white space separated. There are, sorry, I clicked too fast here. There are different delimiters for the catalog, and it accommodates these different types of delimiters. I'm going to browse to the file where my catalog is. I know it has the word small in it, so I'm going to look for it. Where'd it go? Oh, maybe it's in, let's see. It's in here, I think. Yeah. Okay. Okay, so the first thing that you notice is after it's loaded the catalog, it's recognized my ID column, RA and DEC. It did not recognize my magnitude, so I'm going to tell it this is a magnitude. I'm going to tell it this one is, yes, I know, flux uncertainty, not magnitude error, but you have to fix that. It recognized full with half max, stellarity. I happen to have some parameters in here at the end for the reference star selection, just so I can demonstrate it. I don't know if we'll get that far, but here we go. So this is a redshift. I'm going to recognize that because I'm going to filter my candidate list based on redshift. And everything else is recognized that I need. So I'm happy with that. I'm going to give it a name, R. I'm going to select a magnitude to work with. This is not really that important for, I think we're going to be removing these 2 parameters. And magnitudes is what I'm going to specify. Whoops. TU. And then I'm going to click this little button down here that says import. It's going to take 30 seconds or so to load about 10,000 sources. Now it's red, it's got a red X, and this one I'm going to care about a little bit. I'm going to click on it, and it immediately shows the data in the catalog with the working columns that I specified when I read it in. I'm going to tell APT that the catalog accuracy is 10 milliarc seconds. It's calculated for the catalog median, it's calculated a reference point to use. I'm just going to leave that alone. I'm not going to touch that. And then I'm going to say, to get rid of this red X, I'm going to say that we don't need to know about the preimage because we'll pretend we already have one. Okay, so from this parent catalog, I'm going to derive 2 candidate sets that I'm going to work with, a primary and the filler candidate set. And the primary candidate set is going to be based on redshift. They're all going to be based on redshift. So I'm going to make it redshift greater than 5. I'm going to add my filter, select redshift filter, and the minimum redshift is 5. I have to click in another box before I click OK. Now I'm going to click Make Candidate Set. So it's created a list of 344 sources. When I highlight it on the left, the data shows up on the right. Okay, now I'm going to go back to the parent catalog, and I'm going to create a new candidate set, my filler candidate set. And that's going to be everything with redshifts 3 and above. Same way, redshift filter, minimum redshift this time is 3. It's going to include my primary sources, and that's also another little tip for you, including your primary sources and your filler list is always a good practice. Get more observations for free of those. So now I'm done creating my lists, and I'm going to go over to the planner and take a look at the planning parameters that we talked about a little bit. The first thing that I see is this little button for manual planning. Just ignore that for now. I have to choose an aperture position angle. Now, you've done the general TVT for your source, so I'm going to specify one that I know is feasible, 45 degrees. And what I'm waiting for here is the angle here to change in this true angle to target area. And it looks like I'm not connected maybe to the internet. This should come back and return a value here, but maybe that's not going to work. So what that's doing is it's looking to see if that's a feasible angle. It's checking this proposal constraint generator. And if that doesn't work, it's just a problem with the hookup here, I think. I've done it plenty of times. Okay, so now I'm going to specify my primary candidate list, the 344 sources at redshift greater than 5. And, oh, that's why it needs the specification of the primary candidate list in order to fill this in. So it's pulled the PCG, it's found that this angle is feasible. Okay, and this angle is needed for a calculation of the differential velocity aberration that I mentioned before. Okay, so I'm going to choose my filler list. I'm going to leave the 3-shutter slitlet. These are point-like sources. I'm going to select the midpoint constraint for my margin. I am going to nod in the slitlet. It's almost free. Why not? And then I'm going to specify a fixed dither, and I'm going to do a dither across the detector gap to get 2 primary pointings. I'm going to add specification here, and it's asking for, in terms of shutters, how many shutters I need. So in order to do this, you have to know how big a shutter is. They're about 0.251 in pitch, so it's about a quarter of an arc second. And so you can do your calculations. I think I'm going to use, what is 20? Quarter? 80? Yeah, roughly 80 shutters. Hit OK. You'll notice I didn't specify a spatial dither at all. So it's just going to do a dither in the x-axis. And you can add more than one. This is just a little table that keeps track of the different ones. And now I'm going to add a grading and exposure specification, just as you've seen before. I'm going to do a medium band to G235M. I'm going to do 23 groups, with one integration, gives me about 1,000 seconds in each exposure. But because I'm doing a primary dither and a set of nods, I'm going to get 6 exposures, each with 1,000 seconds. You can specify more than one grading here, and it has a set of internal rules about what type of masking to do, etc. You don't have to worry about that. It's done for you. This is where we set up that search grid that I talked about. So most of it is filled in already for you. You leave those parameters alone. I like to do a little bit smaller search grid for my demonstrations, just to show that you can change it. And when you do change it, and I click into another box, it changes the number of pointings that it actually is testing, right? Because I'm using a finer separation in that grid. I do want to use target weights. My catalog has weights, and I want to use them. And I want to create, okay, this is telling me I need a minimum of 2 configurations. It has to be an even number in order to create, a minimum of 2 will give me 1 target set. 4 will give me 2 target sets. So those target sets will have different sources in them. Okay, so I'm going to do 2, just to show you how it works. I'm going to give it a plan name, plan 1. Generate plan. This should be pretty quick, hopefully. Okay, let's see. And now we have, I have to explain what you're seeing here. There are these external scroll bar here, and so you have to have your window pulled out large enough in order to see these internal scroll bars. This first box is a plan description of the plan parameters that we just ran. The second box contains a list of exposures, and they're identified by their configuration number, and there's only 2 because we have 2 primary dither points, so we have a 0th configuration and a 1st configuration. And there's 3 exposures for the 3 nod points for each configuration. So I have a total of 6 exposures, as I said before. The information that you see here is the target set size. That's the number of targets within that particular exposure. Now, not all of them are matched through all the dither points, so you can see different numbers here. There's some buttons here that I'm going to talk about in a minute. I think the next thing I want to show you is that if I just want to find out, for example, I can filter the information of each of these targets. If I click on, for example, this exposure, I see all of the targets down below in that exposure, and this is just a table containing the exposure number showing, we need that for other things. And it shows you that it's used, my highest weight was 300. So it's actually found many of my 300 level sources, weighted sources. If I decide that I want to highlight all of these exposures, you can now see the full table of all the sources in the exposure. And you can filter out just the primary sources, the filler targets, or all the targets. You can see how many of all the targets. If you want to see how many make it to all of the 6 exposures, you say targets in all the selected exposures. So I did the selection with to do the whole selection, I did Command A to grab all of to highlight all of those exposures up there. 5 minutes, okay, thank you. So you get all of the target results below. There's 28 targets that made it through all of the dither points in all of the exposures. But as I pointed out before, each exposure has many more than that. Okay. And let me just show you this button here. This is the MSA configuration. It's going to bring up a little pop-up window showing the configuration. The color green, targets that are color green are the primary targets, the blue are the filler targets, and black is a contaminant that it knows about. Okay, so you can expand this window. It's a little slow. And you can pan, and the zoom is my right mouse button here. I can zoom in on this. And areas that are colored orange here is this basically masked areas created by targets that we've selected, that the tool has selected for us. So it's showing you how well utilized the MSA is by it being colored mostly orange. Let's see. This is a collapse shutter view, which is showing the position of each of the targets in its own native shutter. So you can see, and I wanted to point out, if I highlight a source here, I can go back to this view and see where it is in the MSA. If you hover over a source, you can see the source ID in the upper left column, upper left of the window there. I can layer over and see where all of the targets are relative to, all of the sources are relative to my targets, and I can zoom in on this to see if there are any contaminants in my slitlets. I won't do that. I'll unclick this with a, whatever that's called, Command click. We'll unclick it. Let's see, what else do I need to show? Okay, so to create an observation, if you're happy with the results of your plan, let's say you're happy with this, click that off for a moment. You can say, okay, I like this plan. Well, the next step is to create an observation from the plan. So this is the button here that you would do that. And this is where the observation gets created and the visit structure gets built here. So it tells you that you need one visit to accomplish all of these exposures. Let's see. I don't know why it went to 3,000 for the 2, I guess, for the 2. I'm not really sure about why it expanded this way. To be honest with you, I have to think about that a little bit more. So that's the basic way of utilizing the tool. And I know I need to wind up soon so that you can actually do your example. Your example is going to be much simpler than the one I showed here, but I wanted to introduce all of the concepts to you. If I got to the visit level, if you get to the point where you're doing your program update, I happen to have the columns that I need in here for the candidate reference stars, so I'm going to show you how that's actually done. It's really the click of a button at this point. Okay, so it's not coming up with the reference star bins. I think it's a connection problem, actually. So normally what would happen is there would be a selection of bins that you would pull down from this pull-down menu here. You would select probably the top bin because that's the best one to pick. and it would show you immediately where the reference stars were in the MSA that you for that particular visit. You have to do that for each of the visits at the program update phase. I think that's pretty much it.